Welcome to all. I am Dr. M. Deepa, Assistant Professor, Department of Mathematics in Sri Sanda College for Women. We are discuss about the topic monotonic functions in real analysis. What is a real analysis? Real analysis is a branch of mathematics, of mathematical analysis that analyzes the behavior of the real numbers, sequence, and the series of the real functions. The basic definition for a sequence is a function whose the domain is a countable, totally ordered set. The domain is usually taken to the natural numbers, although it is occasionally the convenient to also consider the bidirectional sequences indexed by the set of all integers, including for the negative integers. Real numbers. The real numbers, the two type of the real numbers. The rational numbers, another one irrational numbers. Rational numbers is the natural numbers, whole numbers, integers. Natural numbers is denoted as 1, 2, 3. Whole numbers is denoted as 0, 1, 2, 3. Integers is the -2, -1, 0, 1, 2 up to etc. The irrational numbers root 3, pi, 0.0, 1, 0, 00, 1, 000 up to etc. It is a real numbers. Next, the definition for the sequence. A sequence AN in a real analysis is a functions from the set of natural numbers. Is the natural numbers is denoted by capital N. The real numbers is the denoted by capital R. That is for each small n belongs to capital N. There is a corresponding the real numbers AN. The sequence can be denoted as A1, A2, A3, A4 up to etc. AN. Next, the definition for the series. A series is the sum of the terms of a sequence. Given a sequence AN, the series associated with this sequence in the expansion of the form of is equal to A1 plus A2 plus A3 up to etc. The partial sum Sn is the convergent as the limit S is the goes to the infinity. We say that the series is the converges to and is the sum of S. It is called the series. The sequence of real numbers. A sequence is an ordered list of the real numbers. Written is specific the orders. Each term of the sequence is the identify the positions or index. A sequence can be is a finite numbers have the finite number is specific the last terms or infinite numbers extending indefinitely. Example of a finite sequence is a 2, 4, 6, 8, 2, 4, 6, 8. It is called the finite sequence or examples. Next, the examples of the infinite sequence 1, 2, 3, 4, using the formula or recursively, where each term of the depends on the previous ones. Some well-known sequence include the natural numbers. Natural numbers means is the one starting from 1, 2, 3 up to etc. of the integers. And the geometric sequence is the like the power of 2 into 1 to 48. Next, the definition for the series of the real numbers. The series of the real numbers is the formed by the adding the terms of a sequence. In the sum of the terms in a sequence, there are different types of the series, including the finite series and infinite series. The example of a finite series is these are example of the finite series. The infinite series are sums that continue indefinitely. Example for the infinite series is the harmonic series. That harmonic series of the terms is the 1 plus 12, 13, 14 up to extra. This is called the infinite series. Is the harmonic series of the terms. In the many cases, the sum of infinite series may convergence to finite value is the convergent series. Divergence to infinity is the divergent series. The study of the convergence and divergence is calculus and real. It is for the used in calculus and real analysis. What's the definition for the real functions? The real functions is the denoted as f from r tends to r. R is the function takes the real numbers from the set of the real numbers is the denoted by capital R is the input values, and other than r is the and assign the real numbers from the r is the output. For formally, a real function is defined by rule or formula that associate the each real numbers is the x is a domain, a subset of R, which is the uniquely real numbers. Y is the codomain, is a subset of the R, is denoted as f of x equal to y. Is then normally is functions as denoted by f from x tends to y. The x is the domain, y is the codomain. It is called the functions. Is the real function is f is to r tends to r. Is the r is the real numbers is the input values. Assign the real numbers is the another r. Assign the real numbers is r output value. Next, the property of the monotonic functions. What is meant by monotonic functions? A monotonic function is the mathematical functions that is the constant in either increasing or decreasing values. Is the input variable or changes. It is called the monotonic functions. The monotonic functions, there are two type of the monotonic functions. The first one, monotone increasing functions. The another one, monotone decreasing functions. The monotone increasing function in the type of the function as the input variable or increases. The function output either stay the same or increases. The mathematically same or increases. That mathematically for any two values x1 and x2, where x1 less than or equal to x2. It is the satisfy the condition f of x1 less than or equal to f of x2 is the monotone increasing functions. The monotone increasing functions, the condition for f of x1 less than or equal to f of x2. The example for the monotone increasing functions, 2f of x equal to x squared is a monotone increasing functions because x is a increases. X is a increases. F of x also increases. Then 2x equal to 2. 4f of x equal to 4. And then value 3x equal to 3. 9f of x equal to 9, which is the greater than is 4. This is the monotone increasing functions. Next, the monotone decreasing functions. In the type of monotone decreasing function, in the type of the function as the input variable increases, the function's output same or decrease, either stay the same or decreases. The mathematically any two values x1 and x2, where x1 the condition for x1 greater than or equal to x2. So it's the satisfy the condition f of x1 greater than or equal also f of x1 greater than or equal to f of x2 is the monotone decreasing functions. The monotone increasing functions, monotone increasing function that satisfy the conditions f of x1 less than or equal to f of x2. Monotone decreasing function is the satisfy the conditions for f of x1 greater than or equal to f of x2. The example for the monotone decreasing functions, the function f of x equal to minus x is the monotone decreasing functions because x is a increases. F of x is a also decreases. When 2x, example for 2x equal to 2. Minus 2f of x equal to minus 2. And then 3x equal to 3 minus 3f of x equal to minus 3, which is the less than minus 2. This is the example for the monotone decreasing functions. The monotone functions, the property of monotone functions, there are two type of the monotonic function. The one is monotone increasing function, is the another in monotone decreasing functions. Next, the statement. Next, the theorem of the statement. Let f be a increasing functions defined on closed interval a comma b, and let x naught, x1, xn be the n plus 1 points, such that the condition a equal to x naught less than x1 less than up to etc. xn equal to b. Then we have proved that the inequality sum of k equal to 1 to n minus 1 f of xk plus minus f of xk minus less than or equal to f of b minus f of b. The next, the proof. The statement is f is the increasing functions. The increasing function defined on closed interval a comma b. In the let x0, x1, xn be the n plus 1 points, such that conditions are a equal to b. Then we have the proof that the inequality these satisfy the conditions. First, the next proof, assume that yk belongs to xk plus 1. The limit points for 1 less than or equal to k less than or equal to n minus 1. We have f of xk plus less than or equal to f of yk, and f of yk minus 1 less than or equal to f of xk minus. So the condition for f of xk plus minus f of xk minus, the f of xk plus the value for f of yk minus f of xk minus the value for f of yk minus f of yk minus 1. If add these inequalities, the sum of telescope to f of yn minus 1 minus f of y naught. Since the condition for f of yn minus 1 minus f of y naught less than or equal to f of b minus f of a, this further satisfy the inequalities. Next, definition for countable. The countable is a set defined as countable if the elements can be one-to-one correspondence. The set of the natural numbers, that is, natural number is 1, 2, 3, are with a proper subset of natural numbers. The proper subset of natural numbers. There are countable set is, there are two type of the countable set. The first one is finite sets. The finite sets means sets with a finite number of the elements is called the finite sets. Example, A, B, C or 1, 2, 3, 4, 5 is called the finite set. Infinite set means, next another one, infinite set. Sets with a infinite number of the elements is called the infinite sets, but whose the elements still be enumerated or listed in a sequence. The corresponding to the natural numbers is called the infinite set. Next, the theorem of the statement, if f is a monotonic on closed interval a comma b, then we have the proof that the set of discontinuous of f is the countable. Next, the proof, assume that the f is a increasing and let Sm be the set of the points. The set of the points in closed interval a comma b, at which the jump of fx is 1 divided by m greater than 0. If the condition for x1, we know that the theorem, if x1 less than, x2 less than, up to etc. xn minus 1 are in Sm, let f be a increasing functions. defined on closed interval a comma b, and let x naught, x1, x10 be the n plus 1 point such that a equal to x1 less than x2 less than up to etc. less than xn equal to b. Then we have the prove that the inequality sum of k equal to 1 to n minus 1 f of xk plus minus f of xk minus less than or equal to f of b minus f of a. It is for the used that n minus 1 divided by m less than or equal to f of b minus f of a. This means that a sum must be a finite set, but the set of discontinuous of f in a comma b is a subset of union of m equal to 1 into infinity. Yes, this is called the countable. Is the next the application in monotonic functions. The monotonic function are function that either never increases or never decreases. They have many applications in mathematics, physics, engineering, economics, and other fields. Here are some of their applications: mathematics, engineering, statics, and data analysis. Statics and data analysis. The mathematics, it is for used for calculus. Calculus is a monotonic function are easy to integrate or differentiate. If a function is known to be a monotonic function, is known to be a monotonic interval, one can easily determine if the maximum or minimum value on that interval. If next the real analysis. The real analysis is used for the monotone convergence theorem. Deals with the convergence of sequence of real numbers. Next by engineering. Engineering system, it is the use the control schemes. The monotonically is the control squiggling in control systems, especially ensuring the stability. A system response should be the predictable and without oscillation for the certain application. Next, the statics and data analysis. This is type of their assumption that response the variable never decreases or increases as the predictor increases. They used for is the applications in monotonic functions. Thank you to all.